Assalamualaikum. My name is Muhammad Zaim Ridwan. I will start our video with introduction and basic principle of the system. Power plant systems are used to generate electrical power and heat. Power plants are multi-component systems with turbines, compressors, steam boiler, condensers, heat exchanger, pumps, and combustion burner. Each operates on a thermodynamic cycle which to produce electrical power. Other fundamental concepts that we need to know are fluid mechanics, which for the pipe and duct size. Next is heat exchanger. It is important in design of condensers, reheater, and others. Due to the multi-component nature of power plant system, the design can be laborious, especially when control system design is included. In addition, significant analysis must be conducted to determine the most economical power plants that will yield the greatest efficiency and performance to deliver a required amount of power. In performance analysis of power plant system, the design engineer will analyze existing power plants and their components to make improvement of the system. How does a power plant works? A power plant converts various forms of energy into electricity using turbines and generators. The heat generated by a fuel source, such as natural gas or coal, is used to produce steam, which is drive a turbine. The spinning turbine rotates a generator, creating electricity through electromagnetic induction. This electricity is transmitted through power lines for consumption. Next is thermodynamic cycle for power generation. There are two types of power cycle. First of all, Rankine cycle. The Rankine cycle is the most uncommonly used thermodynamic cycle for power generation. It is a modified version of the Carnot cycle that includes a condenser and a pump. Next is Brayton cycle. The Brayton cycle is also known as the gas turbine cycle. It's used in gas turbine power plants. In the Brayton cycle, air is compressed in a compressor mixed with fuel and burned in a combustion chamber, and then expand in the turbine to produce mechanical works.
Assalamualaikum warahmatullahi wabarakatuh. Now I want to explain about schematic drawing for gas power plant. The gas turbine cycle, also known as Brayton cycle. So the Brayton cycle divided by three main components, which is compressor, combustion chamber, and gas turbine. For the first one is compression. The cycle begins with compression stage where ambient air is drawn into the engine and compressed by the compressor. This compression process is usually called as isentropic process. For the second one is combustion chamber. After compression, the high pressure air is directed into the combustion chamber where fuel is injected and ignited. The process occurs at constant pressure, allowing for continuous combustion and heat release. The fuel and mixture undergoes combustion, producing a high temperature and high pressure gas. Next, for gas turbine. The hot high pressure gas from the combustion chamber is then expanded throughout the turbine. As the gas expands, it does work on the gas turbine blade, extracting energy from the gas and causing the turbine to rotate. Lastly is exhaust. After passing throughout the turbine, the exhaust gases exit the engine at lower pressure and temperature compared to the inlet condition. These exhaust gases may be discharged directly into the atmosphere or used for additional process in combined cycle system. Moving on to the method of performance analysis. Based on the thermodynamics analysis of gas turbine, these are the shown graph of the data of the gas turbine. Below are the graphs of pressure and temperature, pressure and volume, and the temperature and entropy of the gas turbine. On the right side are shown the table of operating conditions for the streams. Based on the streams are shown in the gas turbine, the values are increasing when it reaching stream 1 until 3. However, in the streams 4 and 5, the values are decreasing. On the left side of the slide are shown the effect of TAM Celsius on GT cycle parameter diagram. Based on the diagram, that are shown all of the graph are decreasing in values except the D graph, which is the effect of TAM Celsius on the compressor exit temperature graph. Meanwhile, on the right side of the slide are shown the effect of ambient RH and PAM on GT parameters diagram. Based on this diagram, all of the graph shown no significant increasing or decreasing value. It is shown that there are constant value except the graph of A, which is the effect of ambient RH on the SFC data diagram.
Assalamualaikum. My name is Muhammad Hazim bin Zawawi. I will explain about the performance calculation of the system. For this part, we have three types of calculation. The first one is we will calculate the mass and energy conservation law. Secondly, entropy generation and loss work. The last one is second law efficiency. Now, I will explain about the first part. The first formula is we use the energy balance. The formula is the change of internal energy plus change of kinetic energy plus change of potential energy equal to heat plus work. The energy utilized for turbine work was determined using equation mass and gravity multiply constant gas multiply temperature at 3 minus constant gas multiply temperature at 4. The next formula is work done on the compressor was obtained by using equation constant gas multiply temperature at 1. The next formula is work net. The formula is work turbine minus work compressor. And then the specific fuel consumption and output of power of the gas turbine will calculate using equation number 5 and number 6. From the formula and calculation, we can get the result for turbine analysis, compressor analysis and combustion analysis. The second part is we will calculate entropy generation and loss work. The entropy across each unit was used to compute for the overall entropy generation S10 using equation number 1. While both entropy and enthalpy across each unit were used for the estimation of the ideal work using equation number 2. The next formula we will calculate the loss work. The formula is T surrounding multiplied with change of enthalpy. And then the fourth formula is we calculate the efficiency of work loss. The result got from the article, it was observed that gas turbine unit record the highest energy loss followed by the compressor, where combustion chamber record 0% energy loss. And such as was the only unit that recorded energy generation. In the compressor, it was observed that 0.9% of the energy supply to the compressor was lost, while 99.1% was adequately utilized. In the combustion chamber, 7% of energy was generated with the chamber as a result of the combustion reaction that took place in the unit. The final part, we will calculate the second law efficiency. In this part, we have two types of formula to get the second law efficiency. The first formula is work shaft equal to work ideal plus total of work loss. The second formula is second law efficiency equal to work ideal divided by work shaft. From the result second law analysis, it was observed that combustion chamber unit record loss work of 248.3 megawatt, while followed by a gas turbine with 77.3 megawatt, while air compressor record as 11.8 megawatt, so that the most substantial amount of energy destruction occur in the combustion chamber.
And finally, I will be presenting about the suggestion of system improvements. Number 1, by enhance the combustion efficiency. The combustion chamber generates significant energy but also cause high entropy and loss work. By improving fuel mixing or using efficiency burners can reduce entropy and boost efficiency. Number 2, reduce turbine loss. The gas turbine had the highest energy loss. Using advanced blade materials and coating can reduce thermal resistance and friction to improve efficiency. And better aerodynamic design can further reduce loss. Number 3, improve compressor efficiency. Even with high mechanical efficiency, reducing compressor loss can improve system performance. By optimizing blade design and improving component precisions to reduce friction and aerodynamic loss can achieve ease. Number 4, by implementing heat recovery system. Integrating heat recovery system like recuperators or regenerators can reuse turbine exhaust heat to improve the efficiency by preheating air entering the combustion chamber and reducing fuel needs. Number 5, upgrade control system. By implementing advanced control system for the compressor, combustion chamber, and turbine can improve performance. Real-time monitoring and control help maintain optimal condition and reduce energy loss. Number 6, utilize combined cycle configuration. Converting a gas turbine plant into a combined cycle power plant improve efficiency by using waste heat to generate steam, which drive a steam turbine to produce more electricity. Number 7, conduct regular maintenance. Regular maintenance and timely replacement of worn components can prevent efficiency loss and ensure that the plant operates at peak efficiency by reducing overall energy loss. Number 8, enhance insulation and lagging. By improving insulation and lagging of equipment and pipelines can reduce thermal loss to enhance the overall efficiency of the power plant.